I was always fond of the fact that music and mathematics are so deeply intertwined, and the most fascinating thing here that on the computer to reproduce some music you have to do it with mathematics only. As opposed to web or game development, coding audio is very challenging because things happen very fast, and like in game development where you have 60 frames per second, here we usually deal with 44,000 kind of frames, though of course these frames are much simpler than game frames. One such frame contains only one single number. Today let's do something very simple, an oscillator that runs on a particular frequency, then we'll play with different types of waveforms. So here is a tiny sound engine I wrote for our experiments. It runs on a browser and takes advantage on Web Audio API engine that gives us all we need, an ability to generate the sound on the fly in real time with no audio input needed, using code only. And by the way, we have no intention to load any sounds, we're going to synthesize only, but no worries, it's gonna be fun. It's written in TypeScript, but it also allows you to code in JS, and if you're interested you can download it. It's published on GitHub, the link below. Let's start by creating a class. Let's call it the cool oscillator. We're going to extend it with another basic class I wrote earlier. This class provides us with a special function called process. All this function does is allows us to manipulate the buffer here. This buffer is a two-dimensional array. First dimension is channels. It can be anything from 1 to, I guess, infinity, but usually it's just two channels, left and right. Second dimension is very long and it contains samples where each sample is allowed to be in a range from -1 to 1. The bit depth of each number is a double precision number, which is actually an overkill because it's a 64 bits number. If you'd record it to CD, for example, this -1 to 1 range would be stretched to cover a range from 0 to 65,000, but integer numbers, which is only 16 bits. So why does the browser waste so much space on us? Isn't it stupid? Actually, it's not. We need the highest precision possible because browser knows that we're going to calculate a lot. These numbers might go through a lot of multiplications, additions, divisions, and after each operation the error is getting worse and worse. But let's get back on topic. A function process and its buffer. So what's the size of a buffer? How many samples are there? We don't know, and we actually don't care. It might be adjusted by the program, by the user, and even changed during the execution. In any case, we have to maintain a continuous and seamless signal, but usually it's from 1000 to 10,000 samples, like from 25 to 250 milliseconds. The longer it is, the easier it is for the system to emit a seamless signal, but the response time suffers if you use it for, say, playing music on an instrument. Shorter buffers eliminate this problem, but introduce another one, sudden interruptions that are perceived as pops and clicks, like on a record, but really harsh ones. So how do we achieve a seamless signal when we know that the buffer can be of any size? We can do it by using so-called state variables that are kept outside the function independently. We'll talk about this later, but first let's see if we can get any sound at all. The easiest way is to generate noise, so let's do some noise. Alright, let's go through the entire array, through both channels. Get the array and put a random number to all of them, like this. Now let's check it. Oh my goodness, that's really harsh. And here is why. We fill the entire range with a random number that changes rapidly, which produces this high frequency signal. It's very unnatural. So to make it more realistic, we have to imagine how a real surface would produce noise. It would move randomly, but not too far away. A surface would take one random step in any direction and will make it generate noise in the entire spectrum as opposed to our harsh noise. So let's emulate it. Let's create a variable outside the function and call it, say, surface, which equals to 0. And then here, instead of applying a huge amount of random change, we'll apply a tiny amount of random to a surface. After that, set current surface state to the next sample. Much better. Now it sounds much softer and sounds like a real noise from real world. Alright, now let's remove this noise and produce a signal. For that, we'll create another variable outside the function that will make sure that we don't depend on the buffer size at all. Let's call it a phase. It will slowly go from 0 to 1, then it will overflow to 0 and start incrementing again, and so on and so forth. So here on every frame I add a tiny amount to our phase, then I check if it's more than 1. If it is, I subtract 1. Please notice I did not set it to 0 because it might contain some value over that 1 and that I don't want to waste. If I lose that tiny value, it might introduce some nasty clicks later when we apply other waveforms. And here I just assign a phase to our current sample. This tiny value that I add to a phase should be real small. If in total we have over 44k samples a second, let's make it as small as this. Yeah, so now we know it will fill the phase in exactly 1 second, right? By the way, we should better use the predefined variable, sample rate, rather than just 44,100, because it can be changed to 48 kilohertz easily. Today it's actually more natural for sound cards to have 48 kilohertz DACs. Some cheap sound cards actually even convert standard CD quality to 48 kilohertz on the fly prior to decoding. Anyway, let's test it. Now we can hear the click every second, and as you can see, it does exactly what we intended to do. It goes up slowly and jumps down instantly. But my sound card and my loudspeakers are unable to reproduce 1 Hz audio signal, neither do my ears are able to perceive it. So let's bring it up to, say, 500 Hz, the tone that can be reproduced by all audio devices on Earth. Since we are playing 1 Hz tone, I need a phase to change 500 times faster, meaning I only need to multiply this value by 500, like this, or even better, like this. Cool, let's hear it now. Perfect, we have a tone, but this shape is a little bit too sharp and it's called sawtooth, but it's not what we need actually. The purpose of a phase was not to go directly to output, its purpose was to keep the phase as its name suggests. Waveforms generators depend on it. If they know the phase, they know what part of the wave to produce at any particular point. Alright, let's try to implement the classic sine wave. First, let's try a naive approach. Let's just take a sine here, pass a phase to it and hope for the best. I can see some traces of a sine wave, but you see it doesn't make a full circle. That's because sine functions accept angles in radians, and we provided it with some 0 to 1 phase, which is wrong. We need to multiply it by 2 pi, and that's exactly what we need. It works. By the way, let me show you what would have happened if we had set the phase to 0 rather than subtracting 1 from it. You hear the clicks? This is what I was talking about. So to wrap it up, let's make a wave swipe up to infinity by adding another state variable, call it a frequency, set it to 500 and replace 500 here with the frequency variable. And now let's change it over time by adding a tiny value. This will make the frequency grow with each sample, so let's hear it. Very well, so next time we're gonna use some other waveforms like triangle or square, maybe some exotic shapes, as well as we're going to draw a musical keyboard on the screen and it's gonna control our synth, so stay tuned.